have any questions about it? The whole secret starts with the charge density on the plate, right? In other words, the amount of charge divided by that area tells you what the raw surface free is. Once you got that, you got the D. And then the D, it starts stroking through air, and it hits the dielectric, but by George, there's no surface charge density there. So the second D in D2 is the same as the D1. And of course, you have the D1 and the D2, you got the E1 and the E2. I'm just down the line like that. And then once you have E, well, then you integrate E from bottom to top, I guess, and you get the potential. Okay, that kind of stuff. And then, of course, once you got the potential, then the charge that I gave you, what was it, 3 epsilon 0 or something like that, divided by that potential is the capacitance. And then once you got the capacitance, then you can get the energy stored, because you know what the essentially voltage is. So anyway, it all tinkles down. It's kind of like dominoes falling. That was the idea of ordering them in the way I did. I hope you saw that, and I hope you did well on this. Okay? All right. Okay, now you don't have to set pen to paper. I mean, all this stuff that I'm talking about is in the notes, but I just want to talk a little bit about it, because right now we're going to start on the second half of the first half of the course. The first half of the first half was electrostatics. Polish that off. We've done that. All right? Now we're going to do some magnetostatics, and I expect I'll spend about, I always say 2 weeks, but I'll bet you I'll spend 3 weeks. So we spent 2 weeks, another 3 weeks, 5 weeks, half the course already on the finishing off of statics. And then the second half will be the dynamics, electrodynamics, which will involve the 4 equations that we're going to be dealing with, coupled together, called Maxwell's equations. All right? So let's get on with the magnetostatics. And first, on this left side, what I've done, and I've done this in the notes, I'm just following my notes, I've pictured what we call the classical viewpoint. In other words, things that you saw when you were a little kid, or you did in high school, or you did in grammar school, where you take 2 magnets, my 2 fingers, North Pole, South Pole, North Pole, South Pole, and you bring them close together, and if it's a North Pole and a North Pole, well, then they want to get apart from one another along the line of sight. If one is a positive and one is a negative, North Pole and the South Pole, they want to get together. Same old that you've done. And I simply picture them here as a permanent magnet and another permanent magnet. It's just that I've called the strength of the North Pole, like for this one, capital QM, and for that one, little qm. Maybe they're different strengths or something like that. So these are supposed to be the strengths of the North Pole. Although we don't know what a North Pole is. What the hell is a North Pole? I mean, like if I had a charge and a charge, a number of coulombs here and another coulombs here, and I was dealing with electrostatics, you know, I kind of know what a charge is. I mean, sort of. But what is the North Pole strength anyway? Well, we're going to find that out. Right, but the point is, the old boys did this sort of experiment, and they found out, by George, if that's a positive North Pole there, and that's a positive North Pole there, they want to get apart from one another, and the force on this one isn't in that direction, it's not in this direction, it's along the line of sight. And then they would, I suppose, say, well, what if I push that a little further away? And they found out, by George, it goes down as the distance squared. And that reminds me of the Coulomb law, I mean, in electrostatics. So basically, the force, let's say on this little guy, is proportional to, I'll talk about that a little bit, to the product, just like in electrostatic, Coulomb's law of business, proportional to the strength of that North Pole times the strength of that North Pole along the line of sight, and inversely as a square. Now understand, this is getting bigger as r minus r1, and this is getting smaller as r minus r1 cubed, but the strength, the length of this and the length of that cancel one of these. So it's inverse square. We saw that kind of writing for the electrostatics. I hope you remember that. So it's just like the electrostatics business. And I say similar to. And similar because, well, this North Pole, he got a South Pole. Now that's why I made these long and skinny like pencils, okay? So that this South Pole and that South Pole are far and don't screw things up. You don't have to worry about that with charges. Here's a positive charge and here's a negative charge. There isn't a nearby, a negative charge here and a positive there, and a positive charge here and a negative close by there. You don't have to worry about that. In electrostatics, it's simpler. Here, so similar, they recognize there's something different about this, but pretty good approximation. All right, that's the idea that they had. Now let's talk about, remember when we talked about Coulomb's law way in the beginning, I had a proportionality constant. The 4 pi is in there only because if you didn't put it in, later on you'd have a whole bunch of 4 pi's and 4 pi's and more 4 pi's. So you get rid of them by putting the 4 pi once and for all in this law, well, in Coulomb's law in the case of electrostatics. And then there was that mysterious thing called epsilon zero. What the hell was that there for? I mean, it was a constant. So why didn't you just call it a constant down here? Well, we saw that epsilon zero was a really important constant. It tells me something about the capacitance per unit distance of empty space. I mean, amazing. And then once I got capacitance, I get the idea, hey, in a capacitor I can store energy. So if I have an electric field in empty space, I can store energy in that place where the electric field is. And that's what the epsilon zero was. Now, the same thing is going to apply in the magnetic world. Now, the magnetic field is not going to be caused by charges and stuff, but by charges moving, currents. But the point is, there's a proportionality constant, the 4 pi again for the same reason as before, but a different constant, and it's called mu zero. And mu zero, it turns out to be convenient. You could put the mu zero here, but it's convenient to put the mu zero on the top. Well, I don't write it on the top. Most books do, but I don't write it on the top. You see that inverse there? I write it like this because I want to have it completely looking analogous to 4 pi epsilon zero. Well, this is 4 pi mu zero inverse, so don't put it on the top, put it on the bottom. You can put it on the top, but I don't do it like that. So it looks very similar to the electrostatics thing that you had before with charges rather than these mysterious things called strengths of north poles or south poles, okay? That sort of stuff. And that's why I put similar in quotes there, because it isn't exactly the same, and the old boys knew that. Now when I say the old boys knew that, if I have a charge and a charge, so let's say a Q and a Q, these are the old familiar charges, you find that the electric field starts on the positive and terminates on the negative. Starts and terminates, starts and terminates, starts and terminates like this. You get a picture something like that. And if you draw them close together like this, I mean, these, and of course this is in 3 dimensions. I'm just drawing a flat version here, like that. This should remind you of layer after layer after plywood. Okay, this is laminated things. Plywood is laminated layers. I think lama means layer. So the layers glued together. They call that a laminar field. Okay, that's the kind of field electrostatic. They start and they stop. Now the old boys knew that if you have a permanent magnet, you have this QM here and a minus QM here, let's say, north pole and south pole of whatever strength, yeah, you get some sort of a, we're going to talk about as being the magnetic field, like this and like that. The thing is, it doesn't start and stop like that. What it does is, if you look into the iron of the permanent magnet, it continues on and it circulates around like this, and this one would circulate on the outside and then go through the same. So it kind of feeds on itself. It's like a dragon eating its own tail, right? There's something different about this kind of a field structure than this. And this one is called solenoidal. In other words, when the lines don't just start and stop, but they continue on and they circulate and come back to themselves. That's a solenoidal geometric field. And they recognized that because you saw that sort of thing if you took a permanent magnet, laid paper on it through iron filings, and you would see this, you would actually see that go all the way around like that, right? You saw those little things line up, and so they did the same thing, and they said, well, that's different from this, but when it's in this sort of orientation close by and those far away, everything seems to be about the same as Coulomb's law, except it wasn't. And I call that the classical viewpoint. So that took us through the early 1800s, okay? Then around 1819, there's this guy, Hans Christian Ørsted. He's a Danish professor, University of Denmark. And the lore says, exactly we don't know. Maybe he was doing an experiment, but the lore says that he was doing like what I'm doing right now. He was doing an experiment in front of his students. And the experiment he was doing was essentially take a loop. Now in 1819, you understand, in 1800, Alessandro Volta, that Italian guy, invented the battery. Until the battery was invented, they had to do everything transients. In other words, charges that discharged, and that was the end of that. But when the battery was invented, well, then you could keep feeding charge, we call that current. You could have current running around in a wire. And so he used that idea. In other words, he put a battery in here, and he had a current running around. And the lore says that, well, it happened that nearby he had a compass. Well, what's a compass? A compass is one of these things. I mean, it's got one of these. It's got a North Pole and a South Pole. So there was a little compass needle. I mean, let's say a North Pole to a South Pole or something like that in the vicinity. And that little guy, when he, I suppose he had a switch in here. When he turned the current on, that thing would turn. I mean. And he was finding that there's an electric phenomenon here, a charge flowing around, and this is a magnetic thing. It's the first time people, maybe they don't know, but maybe other people had seen that, but they didn't write it down. They weren't, how would you say, they weren't mystified enough or something to think that was important. But Ørsted was a very clever man, and he said there's something interesting here, that an electric phenomenon is causing a magnetic phenomenon. Now, I guess he left it at that. He wrote the thing up, wrote a paper, his full professorship or whatever he was doing, and that was the end of it. But then that word got very quickly around Europe. And in 1820, a year later, these two French physicists, Biot and Savart, got together and they said, let's study this very carefully. Let's see more carefully what Mr. Ørsted found out. And so what they did is they said they wouldn't just take a circuit, any old kind of circuit with a nearby detector. But what they did is they said, let's cause this is what I would call C1. Let's make that C1 a real long, straight wire. See, a geometry that is more simple to analyze, or whatever you want to think about. And then, of course, you can't have current flowing on just a wire that's, let's say, 20 feet long, from floor to ceiling or something like that. You have to close it. So I suppose it would be like an experiment where you'd have the straight wire here, and then on the ceiling, you take the wire and go across over there, and then bring it down over there, and bring it over here. So that part of the circuit didn't influence what's going to happen over here. When I say over here, I mean close in to this straight wire. So here's the straight wire, and they're talking about, around here. So that wire over there, the current flowing over there, and the current way up there, and the current way down there, didn't influence what was going on over here. Very little. And that's the idea that you want to give here. So now the current, let's say, is I1. I'm going to talk about this as being circuit number 1 because later on I'm going to talk about Mr. Ampere, very important guy. And I'm going to have a second circuit, so that'll be C2. But right now, C1, carrying current I1. And now I want to point out that normally you say, oh, current's flowing that way, therefore current is a vector. No, don't think of it that way. Don't think about that way. The current, the amperes flowing, is just a scalar quantity, all right? The thing that gives it direction is this guy right here. So this is ampere meters. So if it's flowing this way, basically this is the DL1, like so. You understand? That's what gives it the direction. If it's the other way, then the DL1 would be pointed downward, okay? So that's why the underbar is on that and not on this. And in all the formulations, these will always appear together. They won't appear separate, ultimately. Okay, so then they did that. And then they were, in some sense, they were in a transition. The transition being incited by Ørsted, where there's an electric thing causing a magnetic thing. The magnetic thing being the detector of something happening out there. And this was the Faraday idea of the field. In other words, this current now flowing, we're not talking about charge, we're talking about charge moving. That current flowing is, dare I say it, tensing up the universe. It's just like in the case of charge. Tensing up the universe, we measure it with E. Well, this thing was tensing up the universe, this source, this C1, current flowing on C1, and then the detector of that. Well, let's see, if it was charge, let's say a cloud of charge, tensing up the universe, the mother thing I talked about it, and you wanted to detect that tensing up, what would you do? You would put another little charge in there, right? And there'd be a force on it. You'd measure that, and that'd be measuring the E, basically. That was the detector, all right? This was the mother. In some sense, the parallelism is this is the mother. This is the thing that's tensing up the universe. We're going to talk about it as being the B field, not the E field. And this guy is the detector. It isn't just a charge. It's a charge and its opposite. In other words, a charge of the magnetic sort, a north pole and a south pole. If you put a little charge in here, I mean an actual, in other words, coulombs, wouldn't detect anything. It was the wrong tool to use, all right, the wrong kind of detector. The detector you should put in is this compass needle, which is nothing more than a permanent magnet, north pole and south pole. And that's what they did. So in a way, they were transitioning to ultimately Amperian idea, where instead of having this detector as being the old-fashioned just permanent magnet, this detector is actually going to be another current. So it's going to be current and current, but we're not there yet. So in some sense, this was half. Half of it was electric, and half of it was still the old-fashioned detector, which is a permanent magnet. And what they found, what they expected to find was things like, well, the current's flowing like so, so basically the magnet is going to, you know, the north pole and south pole kind of go parallel or something like that. And they found out, I mean, that's what they expect, sort of like it's being dragged. They talk about it as being dragged by this current along. No, that's not what happened. What happened was, I'm trying to think in 3D here, this is like a circling around the current, I1, DL1. What they found was the little permanent magnet, which I'll say, this is North Pole and this is South Pole. So this is a North Pole and a South Pole. So if that, I should have brought a pencil or something. Why don't I use this? So if this is the current flowing, they found out that the little permanent magnet didn't do this. It did this. Really weird. I mean, it's like that. And not only that, but wherever it went around, it just seemed to circulate around. And if the current was flowing up, like the tip here, like that, then the North Pole was in this direction, going around, and the South Pole was following it. If they reversed it, then just the opposite. The North Pole would be like so, and the South Pole like so. But they would be on this circle, I guess you'd say, and oriented perpendicular like that, not parallel, not like this, like that. Weird. See, they didn't expect that, but that's what they got. That's what they found out. And and like I say, and the fact was that it was directed. In other words, the North Pole kind of, the way we describe this is actually take your right hand put your thumb in the direction of the mother current, and your fingers will point in the direction of this tensing of this B field, and that B field is going to be causing the North Pole to go in its direction. So if the B field is in, for example, the positive charge, magnetic charge called the North Pole will also follow. And then the South Pole will be in the opposite direction, okay? It's just like plus charge wants to go in the direction of an E field. Well, the North Pole wants to go in the direction of the so-called B field, okay? And that's what they found. Now, what they wanted to know was, okay, got that weird direction. How strong is it? So what they did is, I suppose, they took this little permanent magnet, this little compass needle, and they moved it out. And they found, by George, it went down as the inverse square row. Now, I guess I have to stop at this point, but I'm going to go on to the next step and write it the way they didn't write it this way, but I'll write it the way we think about it in terms of the mother current, and then the distance going down as the inverse of pi George square, and then proportional to, and then I will continue with that. Okay? All right. Again, I'm not assigning any homework. Okay? Okay. We'll see you on, what is it, Friday.